In this work, we present a hierarchical representation network for accurate and detailed face reconstruction from in-the-wild images. Limited by the nature of the low-dimensional representational capacity of 3D-MM, most of the 3D-MM-based face reconstruction methods fail to recover facial details. Based on such observation, we decouple the facial geometry into three components: low-frequency geometry, which provides the coarse shape roughly aligned to the input face; mid-frequency details, which describe the details of the contour and local shape; and high-frequency details, such as wrinkles, micro-bumps. Then, in a hierarchical fashion, we model these parts with face-wise blend shape coefficients, vertex-wise deformation map, and pixel-wise displacement map respectively. Through the geometry disentanglement and the hierarchical modeling strategy, we achieve accurate and highly detailed face reconstruction results, taking full use of the abundant details from the input face. As shown in the figure, given a portrait image, we firstly utilize a regression network as the face analyzer to predict the BFM coefficients and obtain the coarse aligned mesh and albedo using the corresponding basis from the 3D-MM database. Combine the image in the coarse mesh, we are able to acquire the in-painted texture in UV space by applying the differentiable rendering. Then we concatenate the position map and the texture map as the input of the following modules for hierarchical details learning. We adopt 2-pix networks to synthesize the deformation map and displacement map in sequence. Taking advantage of the abundant details from the texture T and the pixel-wise learning strategy, we manage to obtain the accurate detail maps which are further employed in a coarse-to-fine manner to generate the detailed face meshes. Finally, combined with the lighting and the refined albedo generated from the retouching module, we accomplish detailed face reconstruction from the single image. Note that the displacement map is converted to detailed normals used in the rendering process in a pixel-wise manner to exhibit all the tiny details. In this slide, we introduce the overall pipeline of the proposed method HRN. Next, we will further elaborate the modules and designs involved in the framework. We propose a novel contour-aware loss to fulfill accurate modeling of the face contour. It works on the deformed mesh and aims to pull the vertices of edge to align the face contour. The contour-aware loss only punish the vertices outside the soft margin of the face and pull them to the face contour, while keeping the vertices inside the face intact. Compared to the common segmentation loss, the contour-aware loss gives a more straightforward direction for optimizing the face contour and is easier for training. The ablation study also reveals its effectiveness. Although facial details can be roughly learned from single image using some reconstruction loss, it suffers from unreality and ambiguousness due to its ill-posed essence. To address this problem, we exploit the 3D priors of facial details derived from the real face scans to improve the reconstruction accuracy. As shown in the figure, given a face image and its corresponding raw scan, we can obtain the ground truth deformation map and displacement map through some fitting processes using the hierarchical representation mentioned above. The obtained detail maps can be used in adversarial training to supervise the domain distribution of the deformation map and displacement map. The ablation study shows that the network without 3D priors produces some unrealistic details. In contrast, the reconstruction results with 3D priors are smoother and more faithful. A face image is the result of a combination of geometry, lighting, and face albedo. Prior works assume that the face albedo is smooth and model it with the low-frequency albedo from 3D-MM. However, the actual skin texture is full of high-frequency details such as moles, scars, freckles, and other blemishes, which bring ambiguities to the geometry details learning, especially in the single-view face reconstruction task. Inspired by ABPN, we propose a retouching module, which aims to generate the face albedo with high-frequency details and facilitate more precise decoupling of geometry and appearance. As shown in the right figure, without the retouching module, the model is more susceptible to the distraction of various skin textures and yields some non-existent details. Thanks to the hierarchical modeling and the 3D priors guidance, we can easily adapt HRN to a multi-view fashion to fulfill precise modeling of the global facial geometry with only a few views by adding the geometry consistency between different views. The figure shows the pipeline of MVHRN. We develop a canonical space and a view-dependent space to respectively model the shared face shape and view-dependent attributes, such as expression, lighting, high-frequency details. Through a fitting process, the face shape is gradually restricted to a smaller and more accurate space under the supervision of different views. Extensive experiments show that MVHRN achieves accurate reconstruction given only a few views of images in less than a minute. To boost the research of face reconstruction from sparse view images, we introduce a high-quality 3D face dataset FACEHD100, which consists of 2,000 high-definition 3D mesh and corresponding multi-view images from 100 subjects. The figures below show an example and the statistics of FACEHD100 dataset. We evaluate our model with several SOTA methods on Facescape and Rayleigh benchmark for single-view 3D face reconstruction task. By contrast, our proposed method can produce high-fidelity 3D faces with expressive details, which are extremely consistent with the original input images. The quantitative comparison also reveals that our approach outperforms other methods in terms of accuracy. In the multi-view scenario, we test the performance of DFNR-MVS, MVFNet and the proposed model given 3-view or 2-view images from Facescape and ESRC datasets. As illustrated in the figure, our model outperforms the other two methods in terms of fidelity, details and geometry accuracy, proving that our framework can be well generalized to both single-view and multi-view tasks. We also extend our method to head reconstruction. Firstly, we combine BFM with Flame and generate a new head 3D model. Then we modify the MVHRN to adapt the new head model by splitting the deformation map into the face deformation map and hair deformation map. Here are some head reconstruction results on the selfie photos. Please refer to our paper for more details. Thanks for watching.